Okay, hi everyone. Hello. Hi, my name is Andre. I'm your head GSI. Professor Fazirani cannot be here today, so he asked me to present the lecture, and it will be about inference. So what is inference? Well, broadly speaking, inference is a way for us to try to understand what we can say about the world from receiving some observations or from making some measurements in the world. What does that mean? Really, we have seen this before in the simple context of balls and beans. Okay, so remember this simple problem from a couple of months ago. In this problem, we have two beans. Every bean contains some number of white balls and some number of black balls. And suppose we are given a ball, say it's white, and we are told that it comes from either bean, but we don't know which one. Can we deduce which bean the ball came from? Well, no, not really, right? Because the white ball could have come from the first bean or the second bean, and we don't know which one it was. But what we can do is we can quantify our uncertainty about the beans. And we do that using this tool called Bayes rule. So how did we do that? First, we write down our prior probability. In this case, let's assume that before making any observation, our initial belief was that the ball was likely to be chosen from either bean with equal probability. So the prior probability is 1/2. And now that we are given this white ball, we can compute the posterior probability, our updated belief after having this observation, and we do that by applying Bayes rule. So here we can invert this probability of the first bean given the white ball in terms of the likelihood of choosing the white ball given the first bean times the prior probability and suitably normalized. Now, if you plug in the values from the problem, you end up with this probability 4/9. What does that mean? Well, that's the updated belief that our ball was chosen from the first bean, and we can also compute that our posterior distribution of choosing the second bean given the white ball is just 1 minus that value, which is 5/9. In this case, 5/9 is bigger than 4/9, so we conclude that the white ball that we received was more likely to have come from the second bean. Okay, so this is just an easy example, and we've seen all of this before, but this is an example of an inference problem. So we are given an observation, in this case the white ball, and there is some underlying process that is hidden from us. So in this case, the hidden thing is which bean the ball came from, and our goal is to try to make some sort of inference. We want to be able to say something about what was the most likely process that generated our observation. Now, in this lecture, we will see how to go from this very simple balls and beans problem into some interesting machine learning applications. So what kind of applications? Let's look at handwriting recognition. So you know that these days there are many systems that can automatically do handwriting recognition. For example, suppose you have a check and you deposit that in the ATM machine. When you do that, the machine can tell us, okay, this is the amount of money that I think you're putting in your check. Is that correct? So in this case, the system can detect that within this blue box, this handwriting corresponds to the value $2.56. So that's pretty cool, right? Because you don't have to actually give the check to someone, and that someone doesn't have to actually read the number, but you can just interact with this machine automatically. As another example, suppose you want to send a mail through the post office, not an email, but an actual mail, and suppose you actually write down the address where you want to send the mail to. And when you put that in the mailbox or in the post office, what happens? Well, these days, the post office has a system that can scan the envelope, and it can automatically detect which address you want to send the mail to. In this case, the system can recognize that, okay, within this red bounding box, there is a number 276. That likely corresponds to the street number. And then within this green box is the street name. And then here you have the zip code 14221. Once the system identifies these three regions, it can try to detect what is actually the content of the box, what are you writing there. And once it does that, the system can then sort the mail automatically to the correct destination, so that this is just much more efficient than having someone actually try to read the envelope one by one. And in some cases, it's actually a lot easier for computers to do this kind of tasks, because really, even for us humans, it can be difficult to try to read some handwriting. So these are very widely used these days, and some of the systems even achieve accuracy that's comparable to human performance. So how do these kinds of systems work? There are many pipelines. For example, here we have to start understanding which one of these region is the most relevant for our purposes. Most likely the name is not too relevant for now. We want to really identify what is the zip code, so we want to send the mail to New York. And once we identify, okay, this is the part that we are interested in, and then we can try to segment these numbers. There are 5 numbers here, and we can try to segment each one, isolate each one of these digits, and then try to do recognition on that individual digit. So in this lecture, let's try to understand this last part. So we want to try to understand the simpler problem of digit classification, and we will see how to approach this using our framework of inference. Okay, so digit classification. What is the problem? Suppose I give you an image, and we assume or we know that this image contains a number, a digit, somewhere between 0 and 9. And our task will be to determine what the digit that's written on the image. So this is a standard problem in machine learning and image processing, and people have worked on this for many, many years, and right now computers can do this task much more efficiently than humans. And the standard benchmark for this problem is what is called the MNIST dataset. It's a collection of about 70,000 images collected from the US Census Bureau and from some other sources. Every image has size 28 by 28 grayscale, so every pixel value is somewhere between 0 and 1. And here are some examples from this data set. So you see that, okay, does this look like an easy problem? Well, we know that every image only has one number in it, and we can assume that this number has been centered and properly normalized. So everything should be roughly on the center, and the brightness value should be approximately the same across all images. And if you look at these examples here, you can recognize that, okay, well, this one is clearly a 0, this one is clearly a 1, this one is clearly a 2. This one looks a bit odd, but you can still see that, okay, this is a 2. This is a 6, even though you cannot see the part that's inside. So for us, it looks like an easy problem. But how can we do this so easily? We, as humans, can do this easily because we have a very good internal representation of what digits look like, and we have all our experience in writing digits. We know what they look like, we know what they correspond, we know what they mean. But if you're a computer, how would you approach problems like this? So let's think about how to approach this problem. So let's start with this observation that suppose you have a very good model of what digits mean. Suppose you know exactly how to generate a digit. So if we have this really good model, then classification should be pretty easy. What does that mean? Well, assume for now that for every digit j, you have some model m of j that can generate all possible images corresponding to that digit. Then if we are given access to this perfect model, then classification is easy, because if I give you an image, what you can do is you can check which one of this model can possibly generate that image. If our model is really good, then there should be only one model that can correspond to that image, and then we just classify the image to that model, right? So for example, here on the left figure, we see a 0, and again, we as humans can know that, okay, that's clearly a 0 because it looks like a 0. it has this circle shape. And if we want to write a 0, then it should look like this, and there should be no way that we want to write a 0 and somehow end up with a 1 on the right-hand side, because they just look completely different. They have completely different meaning. So that's our starting point. So given this observation, let's try to build a model that can generate the digits really well. What can we do? We can start with some simple rules. So for example, again, from our experience, we know that the digit 0 should have this circle shape. It should have only one loop. The digit 1 has this one vertical stroke. The digit 2 looks like this shape, and so on. And you can imagine coming up with a list of these simple rules and try to chain them up together and use that to decide how to classify a digit. But you see from these examples, these are some more examples from the MNIST dataset. You see here that there are just a lot of variations within a digit. You see that we said that a 0 should look like a circle with just one loop, but some people actually do write 0 with this diagonal line in the middle to indicate either because they really write it like that, or because when they write it, somehow their pen just has some extra stroke in it. And when people write 1, it's true that, okay, most of the times you just write it using this one vertical line, but sometimes you write it in a slanted way, sometimes you slant it on the other way, and sometimes people put this thing like this hat on the top and then this stroke at the bottom. And even here you see that, okay, this is supposed to be a 5, but does it really look like a 5? We can see that we understand that it's supposed to be a 5 because we know what else can it be. But if you follow these simple rules, then it's hard to decide if that's a 5, right? And even if the same person writes the same digit multiple times, you tend to see some variations in the result. So if we want to follow this list of simple rules, we have to augment these rules with a lot of exceptions. We have to take into account all these variations, and we have to be able to say that, okay, well, this is an 8 even though it doesn't have 2 loops because the top part is not really connected, but I can see that maybe the person just didn't finish it, or maybe it got cut off in the image or something. And we know that, okay, this is a 7 even though the other 7s don't have this horizontal stroke and this one does. So we also have to add that into our list of rules. And before long, you end up with this really complicated and a lot of simple rules. And at that point, your model just becomes too unwieldy to use. Let's look at another example. What we can do is we can try to look at the curvature of the digits, meaning when we write a number, how does the angle change between points? So this image is taken from a paper from a couple of years ago, and what they did here was, from every digit, you break it down into around 40 distinct points, and you try to measure the angle between every adjacent point. And then you plot that in the graph here. So this is how the angles for the number 2 change, and this is how the angles for the number 3 change, and so on. And then on this graph, on the right-hand side, you see the derivative of the angles, meaning how fast the angles change. And you can try to build this kind of model for every digit, and you kind of see that, okay, different digits have different sorts of behaviors of the angle, and you can use these 2 curves to represent your digit, and then you can try to learn how to distinguish between these 2 curves. How to use these 2 curves to distinguish between the digits that you have. So this approach actually works pretty well, and you get pretty good accuracy, but it seems to be a pretty complex model, and it's not clear if it actually means anything. When we actually write a digit, do we actually have to worry about how the angles change and how fast we want to change the angle and so on? And besides, understanding how to distinguish this curve from this curve, is that really a lot easier than trying to distinguish the actual digits? So, but you can play this game. You can try to build more and more complex models. And if you really want to build a true sophisticated model of the digits, you really have to start modeling the physical process of writing itself. You really have to understand, okay, when you write a digit, how does your hand move? And you have to model the forces between your hand and the paper and so on. But again, okay, remember, what are we doing this for? We are trying to do the task of digit classification, which is supposed to be pretty simple. So can we get away with a simpler model? Can we get away with just something that's really crude, really basic, and still get a good performance? So in this lecture, hopefully I'll convince you that the answer is yes, and we do that from the framework of inference. So let's try to see how we can do that. So what we will do is we will take the probabilistic approach of the problem. So remember that the difficulty of the problem is that we don't have a good definition of what constitutes a digit. We know it when we see it. We know it's a 1 when we see a 1. We know it's a 2 when we see a 2. But we don't have a good, concise definition that can distinguish a 1 from a 2. And we saw that there are just many variations among digits. And what we will do here is we will take all these variations and we will say that, okay, we don't completely know how to characterize these, but let's just take all of them and we will treat them as a probability distribution among the images. So what this means is that for every digit, say digit 1, we have a distribution over all the images such that under this distribution, it's a lot more likely for us to generate the images that correspond to the digit 1. And similarly here, we have a distribution P2 that's more likely to generate the images that correspond to the digit 2, and so on. And suppose we have all of these for every digit. But remember that this is a probability distribution. So even under this distribution P of 1, it might still be possible for us to generate an image that looks like a digit 2, or like maybe when you write 1, it comes out weird. So like this one, for example, you see that it's a 1, but it can also possibly be a 7. And some examples like this 2 can maybe be an 8 or something, but hopefully, if you know that you have the distribution P1, then the bulk of the distribution, where the distribution has the highest value, a lot of that should be actually the images of the digit 1. Okay, so notice the departure from our previous attempt. So previously, we really tried to model how to exactly generate a digit. Now we admit that, okay, maybe we don't know how to exactly generate the digits, but we are willing to accept our uncertainty. We are willing to say that, okay, we just have this model, this distribution that represents our belief about how to generate a digit. So this is an imperfect model, but we see that we can work with this imperfect model because we can use Bayes' rule and we can use this formalism of inference to try to amplify the correctness, the goodness of this model. And in the end, we will see that this actually gives us a pretty good performance. So right at this point, it's still not clear where we get these distributions from. I'm just saying that suppose for now we treat our uncertainty as a probability distribution, but we don't know where it came from. We will see how to learn these models. But for now, suppose we have these distributions. What can we do with that? What we can do is we can view the problem of digit classification as our balls and beans problem. So now, instead of having 2 bins, we have 10 bins. Every bin corresponds to a digit. So this is the bin for digit 0, this is the bin for digit 1, and so on. And we have our prior probability. Let's call that pi sub j for the probability that the digit is equal to j. So this prior probability corresponds to our initial belief about the distribution of the digits. So before we make any observations, before we receive any data, we have our initial belief that, okay, maybe we can say that digit 1 is more likely to appear than digit 2 for some reason. Or maybe people like digit 0, so maybe that appears more likely. So we can talk about how to get this prior distribution later, but suppose for now we have this prior distribution. Then within every class, if we know that we are in bin 0, we have this conditional distribution P sub 0 that we talked about before. So P sub 0 is the conditional distribution of generating an image if you know that the true digit is 0. And more generally, P sub j is the likelihood. It's how likely you are to generate that image x given that you belong to this digit j. So you know that the true digit is equal to j, and then you're just trying to sample from this distribution. Then, just like in our balls and bins problem, what we do when we generate an image is we first choose the bin. So we decide which digit we want to write, and we choose this based on our prior probability. And having decided that bin, say we decide that, okay, I choose bin 2, so I want to generate an image that corresponds to the digit 2. I sample that image from this conditional probability, right? Then if you remember your rule of total probability, what this means is that the overall distribution of the image x that you see is equal to this mixture distribution of all these likelihoods. So with probability pi 0, you sample it from bin 0. With probability pi 1, you sample it from bin 1, and so on. And then within each bin, you sample it from this conditional distribution. Okay, so this is how we connect our digit classification problem from with our balls and bins framework. And now we can ask, suppose we are given an image, a ball, x. So that's our observation. What can we say about which bin, which digit that image came from? But you see that this is the exact same problem as we saw in the beginning. And we know that we can do that by computing the posterior probability of the digits given our observation. So here we apply Bayes' rule again. So here we compute, given that we see this image x, what is our updated belief that x came from the digit j? And by Bayes' rule, this probability is equal to the product of the likelihood, given that you are in class j, times the prior probability suitably normalized, right? And remember our notation is that pi sub j is the prior probability being in class j, and p sub j is the conditional distribution of generating the image from that class. So for example here, suppose this is our prior distribution on the left-hand side, and suppose that we know that the digits are all roughly equally likely, maybe with a little bit of variations, but they should all be pretty equal. So if there are 10 digits, then each one should have approximately 10% chance. And then we are given this image x, right? So then given this image, we can plug into this formula using Bayes' rule, and we get this posterior probability. So here we see that, okay, the posterior distribution actually looks pretty different from the prior. The prior looks pretty flat, but as soon as you introduce an evidence, as soon as you make an observation about the world, you update your belief, and now you have this skewed belief that maybe some digits are more likely to correspond to this image. So given this information, which one is the most likely bin from which x was drawn? Which digit is the most likely digit that corresponds to this image? 5. Why? Because it's the one that has the maximum distribution, right? 5 is the digit where 5 is the digit that maximizes our updated belief about the world from having that observation. And in general, we have this framework where given an observation X, for every possible class, we compute all this updated distribution, all this posterior probability, and we choose the class that maximizes that, and we call that H of X. This is called the Bayes optimal estimator because we computed this using Bayes rule, and we can show theoretically under some assumptions that this is the optimal thing you can do. This is also called the maximum a posteriori estimator or MAP estimator because we obtain this by maximizing the posterior distribution. Yes, question?
Can you explain exactly what the prior graph is showing?
What this prior means?
Yeah, what the prior graph, what is it showing?
This is showing, so we have 10 digits, right? We have digits 0, 1, 2 to 9. And the height of this graph, the height of this bar corresponds to the prior probability of that digit. So here, the prior probability of digit 0 is about 0.1, probability of digit 1 is about 0.12, and so on. So these are the values pi sub j. So these are the left-hand side, the prior, is our initial belief about the distribution of the digits. If we don't make any observations, if we are just told that, okay, in the world there are 10 possible digits, how likely do you think digit 1 appears? Maybe you have reasonable belief that people prefer the digits equally likely, so you think that, okay, digit 1 should just appear 10% of the times, and digit 2 appears 10% of the times. And this can be anything that you choose. And what we are doing here is that given this prior distribution, and then given your likelihood model, you can use Bayes rule to compute this posterior distribution. And even though you start with this pretty flat prior, as soon as you introduce the evidence, you're likely to conclude that some digits are more likely than the others. And we use that to compute this map estimator by finding the digit that maximizes the posterior probability. Okay? Yes?
So to get that probability, would you need something like a dataset that you've already tested previously?
Yeah, that's a good question. The question was, how do we find this prior distribution and the models that we are using? And we will talk about that in the second part of the lecture, but the answer is that for the prior, you can choose it either from your initial belief, from your prior knowledge, or you can get it from some experts. And the likelihood, you can learn that from the data, or you can also try to build some sophisticated model from having some prior knowledge. Yeah, but for our purpose today, we will learn all of this from some training data. Okay, and so here what we have done is we have converted the problem of classification into inference. We are saying that how do you classify an image? What you do is you consider this probabilistic view of the problem, and you do inference using Bayes rule, and you conclude that you classify the image X to the class that maximizes the posterior distribution, this posterior probability, right? So it seems like you need to compute this posterior distribution, but really if you look at the form of Bayes rule, remember this formula, what you're trying to maximize is here, this one on the left-hand side, and you see that the denominator P of X is just a constant that normalizes the probability, so it all sums up to 1. So when you maximize over J, you can ignore this normalization constant, and then you can just try to maximize this prior times the likelihood. So this is actually a big advantage because in practice, when you're looking at some really big complicated problems, the difficult part in computing the posterior distribution is actually in computing this normalization constant. Because you see that to compute this normalization, you need to sum over all possible i's, right? So here in our example of digit classification, there are only 10 possible classes. So you need to sum over 10 possible values. But in real-life applications, you can have billions of possible classes. in which case you need to sum over billions of possible values, and that's just a lot of work to do. Okay, so this is the map estimator. So if we know the prior distribution pi, and if we know the likelihood function p of j, then we are done, right? To classify an image X, we just compute all these products, and then you find the one that maximizes the distribution, and then you just choose that as your answer. But where does this come from? And that's the question that was just asked. So for our purpose, we will use our training data to estimate these distributions. Remember that we are working with the MNIST dataset. So in this dataset, we have 60,000 training examples. Every example consists of a pair of an image and a true label, and we have 10,000 test images. So we can use the 60,000 examples to learn our distributions. How do we do that? Well, first let's learn about the prior. So remember what the prior is. Pi of j is our initial belief about how likely we are to see digit j. So what we do is, if we are given n examples, n is 60,000 in this case, we break these n examples into classes. Maybe from these n examples, you have n sub j of those that belong to class j. Then a really reasonable estimator is just saying that, okay, well, the chance of getting digit j is really just n sub j over n. That's called the empirical estimator. And you can show that this has really good properties. It's unbiased and so on. And from the MNIST dataset, from the 60,000 examples, we see these distributions. So we have 10 classes, and what we get is we see that they're all pretty much equally likely to appear. And this prior distribution is actually what you see in this previous slide. So this is the plot of your prior. So we will use this estimator for our prior distribution. Now the difficult part is actually in estimating this conditional likelihood, P of j. So that's what we will focus on for the rest of this class. So what's the difficulty? Well, okay, so remember that in this data set, we have images. Each one is 28 by 28 grayscale, so every pixel has value between 0 and 1. And we represent every image as this vector in this 784-dimensional space. So it's a vector, it's a point in this very, very high dimensional space. When we represent it as an image, we see that, okay, a 1 looks like a 1 because it has this vertical stroke. But when you try to write it down in this vector representation, what kind of distribution can you use to represent it? So the idea that we will use, and this is a very common idea in machine learning and a lot of applications, is that it turns out we don't really need to model the conditional distributions accurately. It turns out that we can get away with just assuming some very simple, very crude, sometimes unrealistic model. And the advantage is that it's easy to learn, it's easy to estimate, but somehow we can still get a good performance. And that's because we have this tool called Bayes rule that allows us to do this inference procedure. So given our prior belief and given our model, this crude model of the likelihood, we can use some sort of inference procedure to conclude that, okay, this is our updated belief, and we can use that to do our classification. So in this class, we will see two basic models. The first one is naive Bayes. So here we assume that every distribution is just a product of independent coin flips. That means we assume every pixel value is independent of all other pixel values. So whether a pixel value is black or white or anything in between, that has nothing to do with whatever values in the adjacent pixels. So that seems like a very simple, crude assumption, right? Is that realistic at all? No, not really, right? Because when you see an image like this, you see that, okay, this value, this white value, corresponds to this one vertical strip, and this black value appears in the in the rest of the region. So this naive Bayes assumption, it's clearly not realistic, but we will see that it actually works pretty well. So the second model is what we call the Gaussian model. So if in the first model we assume that every pixel value is independent. In the second model, we try to take into account the correlation between different pixel values. So we try to model how likely that a pixel is on or off given what we know about all the other pixels. And we will use what we learned on Tuesday. So on Tuesday, remember, we learned about univariate Gaussian distribution. Here we will use the multi-dimensional analog of that. And we see that because we are taking into account this correlation between the pixel values, the Gaussian model actually achieves much higher accuracy than the naive Bayes model. Okay, so let's start with naive Bayes. So what do? We start by converting our image. So initially we have this grayscale image. We just threshold that into 0 or 1. So if your pixel value is above 1/2, then we say that, okay, your value is 1. If your pixel value is below 1/2, then your pixel value is 0. So that means every image is now just a binary data in this discrete high-dimensional space. So previously it was continuous. Now we go back to the discrete probability land. Okay, does that help? Well, how many possible values are there? So in this big space, there are 2 to the power of 784 possible values, all possible images, all possible black and white images that you can have, right? So if you want to build a general probabilistic model over this big space, then you need to specify 2 to the power of 784 minus 1 parameters. You need to specify all these numbers that all sum up to 1. And this is just a very, very big number. Like, there is no way we can learn all of this parameter. But remember our naive Bayes assumption that within every class, so within every bin, if you know that you're in bin 5, you assume that all the pixel values are independent. So what that means is that this distribution Pj of x actually factorizes into the product over all these individual pixel values, right? And each one of these values, every x sub I, is now either 0 or 1. It's just, it only has 2 possible values. So each one of this distribution is now just a simple coin flip. So that's the simplest distribution we can have. And it's very easy to estimate. And moreover, we have reduced the number of parameters from these exponentially many parameters to just 784 parameters. So that's a big reduction, and that's why this model is very popular, because it's just very simple to learn. Okay, now suppose we are in class J and fix a pixel I. We know that we want to use this distribution, Pji is equal to this value small p if the pixel is on, and it's 1 minus that if the pixel is off. Another way of writing this is using this product. So here xi is either 0 or 1. If xi is 1, then the second term here, the second factor here becomes 0, so you get p sub ji. Whereas if xi is equal to 1, if xi is equal to 0, then the first factor here disappears, and you get 1 minus pji. So this is just a compact way of writing this distribution. So we need to estimate this parameter pji. That's the expected value of this indicator random variable, the pixels, right? And we know how to do that because we've done that so many times in this class. So if we have n sub j examples in the class J, we see how many of those have pixel values that are on in position I. Suppose there are n sub ji of those. Then we just estimate by this fraction. Among these many examples, we see these many values that are on. So we just say, okay, that's our estimator for pji. And remember that we've seen in from a couple of weeks ago that we can show this is actually a really good estimator. It has the correct expected value, and the variance decreases the more samples we have. But turns out in real-life applications, this estimator can have problems, especially if n sub ji is equal to 0, in which case our estimator is equal to 0, or n sub ji is equal to n sub j, in which case our estimator is equal to 1. Why is that? Well, suppose that n sub ji is equal to n sub j, which means we estimate our estimator is equal to 1. In this case, this is the case when among all our examples, all the pixel values at position x sub I is equal to 1. So we always see 1, 1, 1, 1, 1. But what does that mean? Does that mean that it's always 1 no matter how many examples we see? It can be. Or it can also happen that the actual value of p is not equal to 1. It might be very close to 1, but it's slightly less than 1. But just by some random chance, when we see the samples, all we get is equal to 1. And this is problematic because we want to use this estimator to predict about what happens in the future, right? We want to say that, okay, this is our estimator based on our past experience, and then we want to use this to predict, given a new observation, what can we say about that? So even if previously we have seen all examples that are equal to 1, we don't really want to say that, okay, definitely the next one is going to be 1, because what happens if the next one is 0? That happens with no probability at all in your model, and in that case, your model is just wrong. So a way to get around this problem is to use what's called Laplace smoothing, where we just modify this a little bit. So instead of just this empirical fraction, we add 1 to the numerator and we add 2 to the denominator. And so an interpretation of this is that it's as if you have 2 additional samples within class J, where one sample has the pixel value equal to 0, and the second example has pixel value equal to 1. So you see that when you have a lot of samples, when n sub j is very big, then adding 2 here doesn't really change anything, and adding 1 here doesn't really change anything. So for large values of n, this is still pretty close to what we would get under our usual estimator. But in some cases, this actually helps stabilize your estimator and has good performance. And there is also some interpretation of this from the inference procedure, saying that this is your optimal Bayesian estimator if you do your estimation following this Bayesian procedure under a uniform prior on the actual values of p. But let's not worry about that right now. And let's say that, okay, this is how you estimate your individual pixel values. Okay, now that was all the necessary ingredients for the naive Bayes. Now, here's our classifier. So remember that in this naive Bayes classifier, we assume that the data space is this discrete high-dimensional space. So your image is not binary, your image is not grayscale anymore, it's binary. Every value is between 0 or 1. And you still have 10 possible labels, 0, 1, up to 9, so those are the digits. Then from your training data, you estimate the prior, and you estimate these conditional distributions using what we just saw in the previous slide. Now, given an image X, we can compute this is the conditional likelihood of generating X, assuming that it was taken from class J. And remember that the assumption of naive Bayes is that this distribution is the product over all these individual pixel values. And remember that we saw how to write this individual distribution in terms of this product. So then, how do we classify this image X? We use our map estimator. We compute the posterior distribution, and we find the class that maximizes the value, right? So we find the value J that maximizes the product of the prior times this likelihood. But here we are taking the product over a lot of numbers, and each number is between 0 and 1. So when you take the product of all of them, they become very, very small, and eventually your computer will just round that number down to 0. That's called underflow. So to avoid that, instead what we do is we try to maximize its logarithm. So here we try to maximize the log of the prior plus log of the product, which becomes sum of the logs. So this is your formula for the naive Bayes classifier. And you see that it's pretty simple. It fits within one slide, and this is really, if you want to code it up, this is all you have to do. So how well does it work? So when we try to implement it on the MNIST dataset, we got 15.4% error rate on 10,000 test datasets. So that means, is that good? Well, remember that there are 10 possible classes. So if you're just guessing by chance, then you can expect to get about 90% error rate, right? So 15% is actually much better compared to your chance level. And here are some examples of the images that are misclassified. And you see that, so this first image, for example, is a 2, but the classifier thinks that it's classified as a 6. Why? Because under this naive Bayes assumption, this 2 is more likely to have come from the model of 6 than the model of 2. But for us, we know that, okay, well, it's clearly a 2. So how can it be classified as 6? But, well, that's the price we have to pay for making such a simple model, right? But then you see that, okay, this one is actually pretty ambiguous. This one is supposed to be a 7, but even now it's not clear. Well, okay, it's a 7, but it's not a good 7. So we can, yeah, and we can try to go through all these examples and see and learn which ones are hard to classify and so on. But another thing we can do is we can actually peek under the hood and see what this classifier looks on the inside. Remember that we are building this model. We are building this probabilistic model of how to generate the digits. So here are the mean factors for every class. So here are the estimated PJIs for every class. So so you can think of this as the average among all the training examples that are within class 0. This is the average of the examples from within class 1 and so on. And from here you see that, well, they actually look pretty good. Just from taking the average, it seems like we can actually identify what the digit is. But more interestingly, this is a probabilistic model. So these PJIs give us a way to generate examples from this model. So here are some examples. So what we have here is that this is an example that's taken by generating an image from the distribution P sub 0. Remember that P sub 0 is our conditional distribution if we know that we are within bin 0. And this is an example of what we get if we generate digit 1, 2, 3, and so on. And, well, why do they look like this? Remember that naive Bayes assumes that the image is black and white. So you see these black and white patches, and for some digits it's reasonable. So this one is clearly a 0, this is clearly a 1, and so on. But then if you look at this 5, for example, well, you know it's supposed to be a 5 because I've put it in order. But if I just give it to you, can you tell that it's supposed to be a 5? Not really. It's pretty hard, right? And this is a 6, but could be a 0 or something. And here are some more examples, but in some random order. So see if you can try to recognize some of them. Well, this one is 0 clearly, but like what is this one here at the bottom? That's so. What can we say about this model? We know that it has pretty good performance, 15.4%. That's not bad for a first attempt. But we see that the samples that we get are not really representative of what we get from the actual data set, right? So here the top is the samples that we sample from our model, And at the bottom are some examples from the actual training data set. So, and you see that even though we start with these very nice, very structured examples, our model, it manages to capture a lot of the variation, a lot of the complexity, but it's still not a very good model. So we have not really succeeded in finding a good model for how to generate the digits, yet we are able to do the basic task of classification, right? Why is that? Well, there are really two answers to that. The first one is that for our purpose, for this classification purpose, we don't actually need to model how to generate the digits perfectly, because all we care about is how to classify the digit. So as long as we can capture where the peak of the posterior distribution is, we can still find the maximum a posteriori estimator, and we can still classify it correctly. And so that, in conjunction with Bayes' rule, allows us to still do this really interesting statistical inference procedure. And in general, we can try to build a more complicated model that tries to capture more of the structures. And when we do that, as we will do shortly, we see that we will get a better accuracy, lower error rate, but at the cost of having a model that's more complicated, more expensive to learn. And this is just a common trade-off in a lot of problems in a lot of disciplines, where you have to balance between how well you want to build a model, how accurate you want your model to be, versus how complex it is, how easy it is you want to learn. Usually when you increase one, you decrease the other, and so on. So at some point, there is this optimal trade-off. Okay, so before I move on to the second part, the Gaussian model, are there any questions? Okay, so what was the problem of naive Bayes? We really started with this assumption that all the pixel values are independent of each other. And we've said that that's really not a realistic assumption, right? Because when you see an image, usually when you have a black patch, that's more likely to be surrounded by other black patches and so on. And when you see a white pixel, it's more likely that the neighboring pixel values are also white. And in naive Bayes, we just really completely got rid of all of that. We just assume that every pixel value just has no relation at all with all other values. So let's go one step further and try to build a model for the correlation between two pixel values. So now when we want to decide how likely a pixel is to be on or off, we want to also take into account whether the neighboring values are on or off. And here's a brief recap of what we mean with that. So suppose you have two random variables, xi and xj, each one with mean mu I and mu j. Then we can capture their covariance. We can capture their correlation using what is called the covariance, which is the expected value of xi minus mu I times xj minus mu j. What does this mean? Well, if you remember the formula for variance, so we define variance as the expected value of xi minus its mean squared. So that's really saying that this is the covariance of xi and itself. This is saying how likely are you to be wide to be spread apart from your mean. The covariance just captures the same property. Given that you know the mean is at mu I and mu j, how likely are you to that the joint distribution of xi and xj is really far apart from the mean. And we can capture this covariance and this variance structure in what is called the covariance matrix, sigma. So here we have two random variables. So the covariance matrix has size 2 by 2. The diagonal components are the variances of the individual distributions, and the off-diagonal components are the covariance of the variables. And if you know a little bit of linear algebra, you also see that you can write this matrix as the expected value of this. This is called the outer product of this vector times its transpose. Okay, so we will use this property to try to capture our more complicated model. So what is that? So we've said that we want to use a Gaussian model. Here we assume that every image X, now a grayscale image, not binary. We assume that every image X comes from a multivariate Gaussian in this 784-dimensional space. What does that mean? Remember the Gaussian distribution that we saw on Tuesday? In one dimension, the Gaussian distribution is specified by choosing a mean value mu and choosing the variance, how wide you want the distribution to be, right? And the curve for the Gaussian distribution looks like this bell-shaped curve, and this is the density of that. And so what you should notice here is that the density looks like the exponential of minus x squared, centered around the mean value. So x squared grows quadratically, so minus x squared grows down quadratically, and then you take the exponential of that. So the density actually goes down really fast. So you have this very good concentration of your distribution around your expected value. And that's one of the reasons why Gaussian distributions are very popular to use. And this term on the front is just a normalization constant to make sure that the integral is equal to 1. Now, the multivariate Gaussian is just really the high-dimensional analog of this. And here's the formula. It looks a little bit complicated, but what you should keep in mind is that, or at least hopefully what I'll try to convey to you is that this is really the same analog of the univariate Gaussian. So here, suppose we are working in D dimension. So D will be 784 in our case. What we will do is we want to specify the mean factor. What is the expected value of the Gaussian? In this case, here it's mu. And we want to specify a covariance matrix sigma. So we want to say how correlated are the individual directions. And this is a formula for the density, and you don't have to know this, and I'm just writing it for your reference that what this means is that this is really the same quadratic function, but in high dimension. So by the way, so the next few slides will involve a little bit of linear algebra that's beyond the scope of this class, and you should take this just for your own edification, but don't worry about understanding the formula and so on. Just try to get the intuition. So here, the density still looks like a quadratic function, but in high dimension. So here, sigma is a matrix, and here, sigma inverse is the inverse covariance matrix, and this notation here means is the determinant of that covariance matrix. So what I'm plotting here on the right-hand side is the contour plot of the distribution. Each one of these green ellipse is the region in the space where the density has equal value. And we will see in the next slide why this looks like this. But remember that just like in the univariate case, the expected value of the Gaussian is just mu and variance sigma squared. Here we have the same property that if you have a vector x that's taken from this Gaussian distribution, then the expected value is equal to this mu that we specify, and the covariance structure is specified by this matrix sigma. So in particular, the covariance between any two components is given by the components of the covariance matrix, and the variance of each component is given by the diagonal entries of the matrix. Okay, so what do all of this mean, right? So let's look at a very simple special case. suppose for now that all the components are independent with the same variance. That means the covariance matrix sigma is this diagonal matrix with the same entries in every component. So it's just some multiple sigma squared times the identity matrix in D dimension. In this case, if you look at this density function and you plug in this special value for the sigma, you get this simplified density, and you can factorize this into the product over D individual univariate functions. So what this is saying is that each one of these components xi is actually themselves is actually a univariate Gaussian distribution, and this is the plot of the contour. This is the contour plot of the Gaussian. We saw that previously it was an ellipse when we have a general structure. Now, when you know that all the variances are the same, it becomes a circle. And so the density at a point is only determined by how far away it is from the center. And if you've read the note from the previous lecture about Gaussian distribution, we've also seen this kind of arguments when we try to establish that the sum of two independent Gaussians is Gaussian, right? So what did we do there? We look at two independent Gaussians and we say that, okay, the joint density is just the product of the individual densities, and we argue that that joint density has this really nice property of being rotationally symmetric. So this is the same property but in high dimension, that the density of the normal distribution just grows like a ball around the mean value. So this is when all of them have the same variance. Now, if we let them have different variances, then we can stretch this ball in different directions using different values depending on how big we want the variance to be. So if suppose that xi has variance sigma I squared, that means on direction I, we just stretch it according to sigma I. But here again, we see that the joint density can be factorized in terms of the individual densities. So again, it's true that that each one of these individual components is still a univariate Gaussian, now with different mean and different variances. Then to go from this to the final case, we just rotate the ellipse a little bit. So previously, our ellipse is still axis aligned. So these directions, this is the direction of the first axis, this is the direction of the second axis. Now, when we have a general covariance matrix, we rotate that, and now we are allowing this ellipse to be centered and oriented anywhere. And the proper justification of this requires understanding, given a covariance matrix, you can really decompose it into these perpendicular directions, where along each direction, the matrix just acts by scaling. So this is called the eigen decomposition. And so these perpendicular directions are called the eigenvectors of the matrix, and how wide you want to stretch it is called the eigenvalues. But what you should take away from this, hopefully, is that a general Gaussian is really a simple analog of the basic Gaussian, where we start from these independent Gaussian distributions where all of them are independent with the same variance. So you see that the contour plot looks like a sphere, or like a circle in this case. Then starting from this, you can scale it in different directions. So you get this axis, you get these ellipses. And then once you get these ellipses, you can rotate them and get different orientation. Okay, that was a very brief overview of general Gaussian, but suppose for now that we take this formula as the density of the Gaussian. And let's go back to our problem of digit classification. So what we will do is we will assume that within every class J, all the images within that class are distributed according to this high-dimensional Gaussian distribution. So it's specified by a mean vector mu sub j that now belongs to this 784-dimensional space, and a covariance matrix that has size 784 by 784, right? And then to learn this model, we need to estimate this mean vector and this covariance matrix. How do we estimate the mean vector? Well, remember that mean is the expected value of x. It's just the the total average over all your possible values. And if we are given some training examples, then what we can do is we can just look at the examples that belong to that class J and average all of them together, and that gives our estimator for mu hat J. And similarly, covariance matrix, what is that? Well, we saw that it was supposed to be this high-dimensional analog of variance. So it's supposed to be the expected value of your centered variable times your centered variable transpose. So we can also just do that. We can just compute what is called the sample covariance matrix. So here again, we take all the examples in your class. You center that using your estimated mean factor, and then you form this matrix, and then you try to sum them all up together and take the average. So that gives you an estimator of the covariance matrix. So one small issue here is that if you remember, the Gaussian density requires inverting the covariance matrix. So our estimator here is a good estimator, but it might not be invertible, or it might be close to singular. So what people do in practice is they use what is called a regularization. So instead of using this estimator sigma j, you add some multiple of the identity matrix to it. So what it does is it shifts the diagonal components to be strictly positive, and it has the effect of stabilizing your estimator, so that now when you invert it, you get something that's more reasonable to use. Okay, but now suppose that we have this estimator. We know how to estimate the mean and the covariance. Then, just like the naive Bayes classifier, we can form what is called the Gaussian model classifier, where now your image space, your data space, is this high-dimensional real space, not just binary anymore. Now we are in this continuous land, but you still have 10 possible digits, 0, 1, 2, until 9. Then what do? Given some training data, you estimate your prior distribution as before, and you estimate the mean factor and the covariance matrix using what we learned in the previous slide. Then, given a new image X that's now grayscale, not binary, we can compute the conditional log likelihood by plugging in the Gaussian density for this value P of J. And as before, we can just play with the log of that, so that it's simple. So the log likelihood is given by this expression, which looks like a quadratic function of X, just in high dimension. And then, given an image X, how do you classify that? We use the same estimator as before. We multiply the prior times the likelihood, and we find the class that maximizes that. And as before, we know that it's enough to just maximize the logarithm of that, and then we can use our formula here to get this final answer, that this is how you should classify your image under this Gaussian model. Okay, how well does it work? It actually works much better than the naive Bayes. So previously we got 15.4% accuracy, 15.4% error rate. Now we get 4.5%. And here are some examples of the images that are misclassified. And some of these are still pretty, or should be pretty easy, like this one should be a 2. But we see that some of these are actually pretty ambiguous, like this one, this 7. It's misclassified as a 1, but you see that, well, it's reasonable even for us to think that it can be a 1. Or this image here, that's a 9 with a very small loop. So the classifier thinks it's a 1, and it's pretty reasonable, right? So yeah, so you can actually go through all these examples and see that the ones that are misclassified are actually pretty ambiguous. And as before, we have a probabilistic model of the digits, so we can look under the hood and see what it looks like inside. So here at the top, this is the mean factors of every class. So this is what we estimate the mu j's to be. And again, this is just the average of the digits. So it looks the same as our previous naive-based classifier. But now we have more structure, right? We also have this information about the covariance matrix, how likely we think every pixel is correlated with any other pixel in every class. So on the left-hand side, here you see the sample covariance matrix of the class 0. And on the right-hand side, you see a sample covariance matrix of the class 9. So you can make some just visual judgment and see that, okay, well, they both look like they have this interesting cross pattern here. And the class 0 looks like it has this square shape, whereas the class 9 looks like it has this more round shape. But do this make sense? How do we understand what this means? And that's a pretty hard question to answer, because once we go to this high-dimensional space, we tend to lose a lot of our intuition. And in this case, the matrix is 784 by 784, and it's really hard to make sense of what this possibly means. So that's a general theme in a lot of problems that you have, that in lower dimension, then you still can use your intuition to guide how you should approach the problem. But once you go to this high-dimensional model, once it becomes slightly more complex, you see that, okay, it works pretty well. It's 4.5%. But really, do we understand what this means? And that's a very hard question. But as before, we can also generate some samples from this model. So here, again, so the top two rows are just examples, actual examples from the training data set. The next two rows are examples that we generated from our Gaussian model. And we see that, okay, you can sort of recognize the digit in each one. And then the next two rows are more samples from the model, but now in some arbitrary order. And it's actually a lot easier to look at it from far away, and you can sort of recognize that there is some faint shape, and you can identify the digits, although maybe this one is a little bit difficult to understand what this is. But you see the qualitative difference between this one and the naive-based model. In the naive-based model, we assume that every pixel value is either 0 or 1, so you get this really discrete-looking set, like these black and white patches. But here the images, the samples that we get are just really noisy. It looks like these grain values, and even more worryingly, because we are working with the Gaussian distribution, it's distributed over all of the real space. So the pixel values can actually be negative. And does that even make sense? And we can say that, well, we can just ignore the negative values, or we can just shift them all up to be positive and so on. But again, that's a question of, how well does this model actually understand the problem that we are trying to answer? Okay, so some takeaway points. So in this lecture, we've seen a possible way to treat a classification problem as inference. And we did that by adopting this probabilistic view of the world. We are trying to say that, okay, we are given these images and this task. Now let's suppose that these images are generated from some underlying probability distribution. Then we just need to try to model these distributions, and we use the formalism of inference. We use Bayes' rule to help us do our classification. And we've seen that we can make some really simple, some really crude model that doesn't really correspond well to the task of modeling digits, but it still works reasonably well. In the naive-based model, we get 15% error rate. In the Gaussian model, we get 4%. And the reason for that is that, well, one, this digit classification problem is actually a pretty easy problem. That's why this is a good example for introduction to machine learning. But second, we have this really nice framework of inference. Even if we start with some probabilistic model that's not too realistic, we can still use Bayes' rule to try to build our inference mechanism And after that, we can do whatever we want with the posterior distribution. So where do we go from here? So after these very simple models, we can try to take one step up and say that there is this formalism of probabilistic graphical model, which is a very interesting, very beautiful marriage between graph theory and probability theory, where we try to model the correlation or the connections between random variables using the structure of the graph. So in our case, the naive Bayes model assumes that all the random variables are independent. That corresponds to having a graph with n vertices that are just completely disjoint, so they don't have any edges. But here you see some examples of graphs that are used to understand some real-life problem. So for example, this two-dimensional grid, it can actually be used to understand our digit classification problem, because here we can say that, okay, every one of these nodes corresponds to a pixel value, and these edges mean that a pixel value can be correlated with adjacent pixel values. Whereas here, this multiscale quad tree, this represents this hierarchical approach that if you want to try to analyze some image or some data, what you can do is you can try to analyze each one of them in small patches and then try to combine them together in small patches, and then you can recurse on that, and you can build this in multiple layers. And in this formalism, the way to do inference is still using Bayes rule, but now it's a lot more complicated, and the algorithms actually depend on the structures of the graphs, and that's why, this is one of the reasons why we introduce you to the formalism of graph theory and also probability theory. Thank you, and I'll be happy to answer any questions.